All right, welcome back to the coronavirus series here. For those of you that are watching from home. Okay, so in the previous lectures, we talked about building a tree from traversals. And we said that we can build a tree from a level order traversal. So for example, if we have something like this, maybe one more letter like that, we can, and this is not technically a binary search tree, it's just a binary tree. But the level order traversal of this is going to be A, B, C, and D, right? And we can build a unique binary tree from a level order traversal as long as one specific sort of situation is met. And that is that it's a complete tree. Now, this is not a complete tree. If it was a complete tree, it would mean that everything but the last level is full, and the last level that's not full is going to be everything moves to the left. So for this to work, then D would have to be on over here. Now it's a complete tree. And the traversal is this, and you cannot build any other tree as long as you know that it's a complete tree other than this tree. However, that's not what we had. What we had was a D here. So the workaround that we found to sort of make any tree into a complete tree is to sort of put placeholders for that. And we used a wildcard. We used a percent in assignment 6. And we said, okay, we'll just put that in, and then we're not really going to insert that when we're actually inserting, but using that, we can then go ahead and actually do the right traversal. And now it's unique. Now this is guaranteed to give me this tree. It will not give me any other tree, right? If I don't do that, if I just do A, B, C, and D, then I could have any sort of combinations here. I could even have a degenerate tree that goes A, B, C, and D like this, right? Because this will give me the same level order traversal, right? So that's why we use the percentage placeholders. Okay, so that's how we've been doing it so far. That's how assignment 6 works. Now, I don't like having to have these wildcard characters or forcing it to be a complete tree. It's a lot of extra space that I have to add to potentially. And today what I'm going to show you is an algorithm that can build a unique tree from a traversal. However, there's a catch. You need more than just one traversal. You need 2 of them. And not all combinations will work, as you will find out in the assignment 7. But the ones that will work for sure, and I will show you, are using a combination of the in-order traversal and the post-order traversal, and the in-order traversal and the pre-order traversal. And as long as you have both traversals, you can build a unique tree. And it's sort of like the intercept of them that makes that tree unique. So before I just show you sort of the systematic way of doing this, I want you to understand why this works. And so to do that, the first thing that I want you to think about, and here, let me move this out of the way. Or here, actually, we'll just copy these down, copy the list down. Well, I never wrote this, but this is the in order. Let's take this, copy pasta. Okay. What can you tell me about the first element of a pre-order traversal? I heard it, I think.
It's a leaf.
It's a what?
A leaf node.
Actually, the complete opposite.
So it's the root node.
It's the root node. Pre-order. For the in order, it could be the root, or it could be a leaf node, potentially. If it's a degenerate tree, then it's going to be the root, too. If it's not, then most likely it'll be a leaf node. Yeah. The leftmost leaf node. So, in the pre-order traversal, the left node, the first node, is always going to be the root node. That color looks different than here. Here it's green, but interesting. Let me pick something a little darker. Actually, you can just... All right, whatever. Whatever that color you see is yellow, I see it as green. So the first node of a pre-order traversal is the root node. So in the in-order traversal, we can identify that node as long as the nodes are unique. If there's duplicates, this whole thing breaks. So that's, I guess, the one catch to this. So as long as they are unique, then we can identify it in the in-order traversal as it being found as the 4th element. Now, knowing this, what can I claim about the elements before 21 and the elements after 21.
Left and right.
That's right. Everything on the right of 21 is going to be also on the right of 21 in the tree. And anything on the left of 21 is also going to be on the left of 21 on the tree. Meaning that the tree this will build will have, as we said, 21 as the root. And then it will have 44, 11, and 32 over here. And here it'll have a 55, 39, 96, 22, 66, and 69 over here. We don't know what order they go in yet, but we know that they go on that side. We're not gonna find the 55 on the left side of 21.
In order to rebuild this tree, would you have to first specify if it's full, complete?
Nope. In this case, you don't. In the level loader one, we did. Here, it'll work for any binary tree.
Okay.
It could be a degenerate tree, it could be a full tree, it could be perfect tree, complete tree, anything. That's the cool thing about this, and you don't need any sort of wild cards either. So, okay. So, within the 44, 11, and 32, let's kind of look at this closer. Looking at these numbers closer, what combination could they make? Well, suppose that I said that 11 was the... Actually, before I even tell you what the root is, what combination could I make here? Well, I could have something like this. There's a lot of them, I think. We could also have... Actually, could that work?
Yes. No.
Why not?
The 44 is bigger.
That's right. The 44 is... well, you said... The 44 is on the left side of 11, meaning that the 11 has to go after 44 in the traversal. So that will not work. Good catch. Is this okay? Yes, because the inner traversal of this will give you this. What other things could this be? Well, it could be 11, 44, and 32. It could also be 44, 32, and 11. That could work as well.
Can it be 32, 11, and 44?
Yes, I was just thinking about that too. Are there any other ones? I don't think so. Yeah, there is actually one more, I think. If we make 32 here, 44 maybe there, and then 11 here. Yeah, that works too, right? So there's at least that many. Maybe more. Don't really feel like thinking about it. But I know that these many will work, right? So, which of these is it? Well, to find out, we need to know which is the parent node of these and which are the child nodes. So which is the direct descendant of 21? Who's like the direct child of that? We don't care about the grandchildren. We care about who the child is. Well, if we look at the preorder traversal, remember, the preorder traversal is going to be the root first, then left and right. Meaning that as you recurse down the tree, the moment you visit a node, the first thing you do is you print it in the traversal before you go to the children. Because of that, in the preorder traversal, I see the number 11 before I see the number 44. That means that I visit 11 before I visit 44, meaning that it must be the direct descendant of 21 if we visit it first. So 11 must be the child of 21. 44 cannot be the child of 21 because if it had been, we would have visited first. Because if we have something like this, 21, and then we have 11, and then we have some 44 later on, we would have, whether it's here or here, it doesn't actually really matter if you think about it.
Yeah, I was going to say, is 44 could be possible like a child of 11?
It could be, yes. In fact, it will more likely than, it may or may not be. We'll figure that out later, because it might actually be, 44 could potentially be here. We don't know yet. We have to look at the in order for that. But that's not what we're looking at yet. All I want to say is that, at least on the left side, 11 has to come before 44 as a child. And then 44 can be a child here, here, or maybe even here, but not on the left side of 21. because we see this first. And if we remember that preorder means that you have to visit the root first before you print it out, then that kind of gives that away. So because of that, we can highlight this in a different color as the next root that we're going to see. And that means that that is going to be the child. So that means that it's going to be this case. Okay, so looking at that, we're looking at the subtree. On the right side, we have one number. On the right side, we have 32. And on the left side, we have 44. And both of these are to the left side of 20, right? Because they're on the left of 20. But within it, this tells us that 44 is going to be the left child and 32 is going to be the right child. I mean, because they're only one node each, then that's just the direct value. It's not a set of them, as it was before. Which is how we basically got this. So ultimately, our tree is going to look like this. I'll put another one here, so you have the history of it. Like that. The next number that we look at is actually 44, technically. Now, 44, even though we already printed it, we're looking at 44. But here's the thing. The parent of 44 is 11, right? So is there any numbers between 44 and 11? No. We'll call those L. And any number over here, we'll call that K. It turns out that because there's no there's no values in K and L, that's why 44 is a leaf node. And it has nothing. So here would be K values and here would be L values. That's just so that you'll kind of start to get the algorithm. Then we look at 32 and the same thing happens. Oh. Oh, we already used that color. Map problem here. As you can see, there's nothing there for the L's and nothing there for the K's. And that's why, again, that's a leaf node. This, of course, seems redundant because you saw there's only one thing. But, you know, when you're coding this, these are the kind of things you got to check so that you can stop the recursion. Moving on to 55. That's a little bit different now again. Because that's the first value that we're seeing on the right side of 21. Again, we can think of our L and K's. Our L are these values, right? The left side. I guess I should have used R and L to make it less confusing, but whatever. And these can be our K values. So again, these are the right, and you can think of this as the left. What does that mean? Well, that means that the next tree is, and I'll rewrite it just to make it look nicer. It's going to look like this. Oh, I was like, I'm seeing a whole different tree over here, but that's not the one for this class.
Thank you.
All right. Next thing to look at is going to be what?
39.
We always keep going with the preorder.
69.
So 69, yes. So where's 69 over here? It actually is all the way at the end here. So that means that, again, our left side in this case is going to be empty. And then the right side is It's going to contain all of those. Oh, the screen got dirty. The coronavirus coming in. No, I'm messing. So, 69 is there. So therefore, I guess I'll copy paste it. That means that all of these are going to go to the left of that. Okay, that's not what I meant to do. There we go. Are we understanding this so far? Let's copy the list down so that we don't have to keep scrolling up either. Okay. The next number that we're going to look at is the 66. Again, we're working our way from the beginning of the preorder list all the way to the end. 66 is going to be the next root. It's found at the end of the list. That means that 39, 96, and 22 are actually going to be on the left side of 66. Like such. Moving on to the next one, 96. That's a little bit more interesting because the left sublist has one element in it, 39, and the right sublist has one element in it, which is 22. I don't think that's the right color. Okay. So because this is going to be the root here, that's going to be the left child, and that's going to be the right child. And that will pretty much wrap it up for this example. As you will see here. And there we go. And so if we go, and how do we know that we're done? Well, technically we are not done yet. After we look at the, there we go. After we look at the 96, we still technically look at the 39. But again, there's nothing here and there's nothing here in this individual. No, we look at the 22. There's nothing here. There's nothing here. And then that's when we properly are done. If we verify the tree with what I drew originally, you would see that is the exact same tree. So that means I did my traversals right when I was doing it. Questions about that?
How did you, can you go back to the 69 again? How did you determine that one was on the right?
So we finished 55, and then when we finished 55, that's the first thing that was on the right side of the tree from the 21. So that means that we were looking at the list from 55 all the way to 69. And then we went to the 69. The 69 is at the end of this sublist. It's kind of like quicksort when the pivot was the biggest element kind of thing. So when it's dividing it into two sublists, kind of like quicksort does, in this case, 69 has nothing on this side before the end of the entire list, and it has 39 to 66 on this side. So that's why 69 has no children here, and it has all the children over here. So, yes. But, cool. Other questions?
How did you come up with the original, initial list?
The traversals?
Yeah.
Well, that's what I'm saying. Somebody will give you this and be like, build a tree out of that. So in the assignment, the encrypted messages from Spectre are basically an in-order and a pre-order list, or an in-order and post-order list. And what you'll do is, instead of you building the tree from the level order, you build it from those two traversals, and then you'll do all your traversals again from assignment 6, and one of them will give a message.
So you're just giving those two lists.
Yes, you're given those. Yep. So now you know how to do in both directions. If I give you something like this, and I tell you in a test, like do the traversal of that, like do the post-order traversal from that, you can do it. You can also, given the post-order and in-order, build the tree itself. And you get both kind of questions in the test. So let's go ahead and do an example with post-order now, since this was pre-order.
What's the time complexity of something like this?
I would literally be trying to figure it out.
Okay, well, each of this runs n time, right?
Right, because pre-order goes.
Pre-order goes n time, and then for each of the inserts, log n.
So n squared log n?
Not in squared, definitely not in squared. I'm thinking if it's n, if it's just n, or if it's n, it's supposed to be n log n, but I'm happy just n. I'm trying to. This runs. You have to check the entire list, but you only check log n. Yeah, n log n, I think. Should be n log n.
It's very similar, like the,
It feels like Quicksort almost.
right, because it's just, the only difference is you're dividing it, you're doing -1 for the current root. And then
But
you're
what if
dividing
it's
by
a
2, and
degenerate
you're doing
tree?
that.
Then it's gonna be n squared for a degenerate tree, baby.
Right, in the worst case.
It's gonna be like Quicksort with n
Your
squared.
root is your first thing in your in order, and then you just keep, it's like the worst case of quicksort.
Yeah, yeah. So I suppose that n squared and theta and omega are going to be n log n. That makes sense.
Question on the test, or we gotta do time complexity for correct?
On the final, maybe, not on the midterm. On the midterm, you will have to grind these out and do them by hand. Like it's just the fact of life. I'll give you these and be like, build a tree, or I'll give you the tree and be like, give me the traversals.
So you're not gonna do what you did on the last one, where we gotta build the tree, do all the math for it, worst case scenario, best case scenario. You know how you had like 7 parts for one drawing question?
Wait, what?
You don't remember that? You wrote the test.
Which test? This class?
Yeah.
You drew a tree? You mean like merge sort?
Or yeah, where we would draw those out and then we would.
Yeah, but that's merge sort. It's just one tree you're drawing like blah and then blah.
Right.
It's a diamond. Here, wait until you get to ABL trees. You're gonna draw the same tree like 20 times in the test. Now that's what you'd be worried about, actually. Drawing the same tree that many times. Actually, here you gotta draw the tree a couple of times, right? Too.
Yeah.
Yeah, so that's the one you gotta be scared about. Okay, so I haven't done this for any example, but we're gonna. So I'll tell you what I'm doing. Let's stick with something small.
Should we expect our exam rate pretty soon already as well?
Expect your exam rate to what?
Should we expect it pretty soon as well?
Exams?
Yeah.
You're gonna get them back in about 20 minutes.
Oh, bro?
Yeah.
Nice. Finally, I've been waiting for you. I want to see how bad I did.
I do not, but I do know that somebody in this class got 115%, 16%. Yeah.
I know.
Hell yeah.
They are not an accurate representation of.
It's probably most likely. He gets 100% in every exam.
It's hard to come up with a tree.
Are you writing something?
Yeah, but it's a tree that I don't, see if I give you the tree, it's kind of boring because you know what it's going to look like. So I'm doing the tree beforehand and then we're going to figure it out. It's more interesting that way. I'm just trying to come up with a cool tree. Okay, the tree has been generated. Traversals are going to be generated now. So let's do the in order one first. E, I, T, no, not T, 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 there we go. E, I, T, T, G, 3, V, S. Okay, so that's the first traversal. Yeah, I'll do the second one. And then for post order, it's going to be left, 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 left. E T T I 35 V G 2468 2468. Okay. So E T lowercase t uppercase T I 3 S V G. I guess I'm mixing numbers and letters. Do not be scared. It doesn't really matter as long as it's just a stick. Think of it like a stick. It's an I, but it doesn't really matter. They're all unique, so that's what matters. Okay. Guess what? It's going to be the exact same algorithm as before with one tiny little catch. And that is, instead of starting from the left and going to the right, you're going to start from the right and go to the left. Why? Because what is the root in the post-order traversal? The last element, which is, in this case, G. So already we can say that we got 3V and S here, and here we got E, I, T, and T. And so we're going to work our way that way. And again, I guess in this case we'll use green for this side. These are the smaller numbers. Or it's not smaller, sorry, the left numbers or left items. And then we'll use brown for the right ones. So the next thing we're going to look at, because we're working from the end to the beginning, so size minus 1, we're starting from there, I suppose, if you think of this from like an algorithmic point of view from C++, is going to be the B, as in Victor. That looks too close to the brown. At least on my screen. Let's use that. There's our V. What does that mean about the 3?
It's on the left.
It's on the left. What about the S?
It's on the right.
It is indeed on the right. So if we go ahead and regenerate a tree, V's on a root, 3's over here, and S is over here. And here we don't know anything yet, because we haven't gotten there yet. Next, we are going to go ahead and look at the S, but we already kind of saw that there's nothing here and nothing here, so there's no childs. Then we look at the 3, and similarly, there's nothing here and there's nothing here, so that's just a low, as you see, it's a leaf node. Nothing interesting there. It gets interesting when we get to the I, or 1, or whatever that is. Where's that at? It's the second element here, meaning that this is smaller, and this is bigger, and that's our root, right? So, bigger, smaller, and the root. Okay, so let's go ahead and redraw that. Okay. Next, we're going to look at the T. So right now, we got 2 T's in there, right? But it could either be like, it could either look like this, coming from the I, with a T there, and then the T here. Actually, no, it couldn't look with a T there. It could look on that side like that. But it could also look like this, right? It could be one of those two. But because we see that the T is next here, the bigger T, that means that's going to be the parent of the two. So that's going to be the parent. Meaning that it has to be this. Ooh. It has to be this example, and not that one. Okay, let me read. I don't like how that looks. That's it. Because I mean, technically we're not done, but you know, we'll look at the lowercase t, which is the only thing on this side. There's nothing on this side, so there's no right child to t. There's a left child, which is the lowercase t, and looking at that one, there's nothing here for children. Same with e, there's nothing. So that's when you're actually done. So what's the level order traversal of that?
Now I have a question.
Yeah, go ahead.
How come the big T wasn't the parent then? Because I was looking at it from right to left.
Well,
the big T goes, oh, but
yeah.
in the post order.
Yeah, in the post order is the one you want to look at. Don't look at in the order one for that one. The post order is the one that decides who is whose parent, basically. The in order just figures out left or right side.
Okay.
And the combination of that is what gives you. Other questions? So what's the level order traversal of that say?
GIVETS.
Yeah, but what does it mean?
Give test.
Give tests.
I didn't even see that.
Yeah. Well, I was trying to make it unique, so I had to use the three there. I could have used the 1 there. So okay. Are we good then on this? Can we do assignment 7 now?
Maybe.
This algorithm is easy to understand. It's a little bit tricky to implement, to keep track of like the sublists and things like that. Think of quicksort. That's kind of the style of it. So, you know, you'll have to keep your left and right sublist pointers, you know, and then you keep the preorder array pointers, so you can go through all of that. And then when the sublist becomes less than 1, you don't want to recursively call again on that. That's when you actually insert it. It's a little bit tricky, but I have faith that you guys will be able to do it. So, okay, if there's nothing else, then I will go ahead and stop the recording. So, I guess this is it. Spring break after this. Oh, no, we have one more class. Yeah. So next time we'll talk about ABL trees.